together to we can try together to go through the K groups of Z mod 25, for example. And by we go through, I mean the computer will do all the work for us. It would be too hard to do on our own. So, okay, so let me just start with something about K theory. And please interrupt with questions, or if stuff on the board isn't clear. As you see, I pre-wrote this, and hopefully it's not too small. I can potentially try to make it bigger. So Grothendieck introduced K theory, I don't know exactly when, sometime in the 50s, I suppose. And what you do is you take all finally presented projective modules over your ring. That forms a monoid. When you take isomorphism classes, the monoid structure is given by direct sum. The zero object is the zero projective module, and you group complete that. You just force it to be an abelian group, and that's K0. This is very important. It's a very important object. If R is a ring with some kind of geometric flavor or meaning, this Grothendieck group is closely connected to Chow groups, especially rationally. So it carries a lot of interesting geometric information. This is not a talk about K0 though. For us, K0, all of our rings are going to be local rings, or PIDs even, or valuation rings, or quotients thereof. And in that case, K0 is always just isomorphic to the integers. There's a natural rank map just given by taking the rank of a finally projective module, and that induces an isomorphism. So there's not really much to say about K0. K1 is a little bit more interesting. What you do is you first form the infinite general linear group just by including invertible n by n matrices by adding more and more ones. And you take the colimit of that process. That gives you the infinite general linear group. Inside that group are the group of matrices corresponding to elementary row or column operations. So with coefficients in your ring. So those are rings that are one on the diagonal, and they have a single, possibly non-zero off diagonal entry, which is this, just given by some symbol E, I, J, and then upper A. That means we put A in the appropriate place. And we form this quotient. So it turns out that that this is basically the largest, how do you say, normal perfect subgroup. And so this quotient is in particular abelian, and that's K1 as defined by Bass. And if R is a local ring or a field, this K1 group is just the group of invertible matrices. There's a natural, invertible elements of the ring. There's a natural map from GL1 to K1 given by taking the determinant. And the determinant of any of these elementary matrices is 1. So we certainly get an induced map from K1. And in these cases, that map is an isomorphism. I'm giving a little bit of this background, maybe to, well, okay. So K2, we do something kind of related. We look at the group of elementary matrices. And I'm not going to give the exact definition, but you take a free abelian group on symbols, or sorry, not free abelian, excuse me, a free group on symbols just corresponding to these, that they're just formal symbols X, I, J, A, where I is not equal to J and A is some element of the ring. And you just write down the most obvious relations satisfied by those in ER, this group of elementary matrices. That gives you some set of relations, corresponding to how, what happens when you iterate row and column operations. And you just take those relations and you quotient out this free group by those relations. This then admits a map to the group of elementary matrices, and the kernel is K2. So K2 is somehow measuring the defect of those easy relations to tell you everything about the group of elementary matrices. And starting with K2, things start to get a little complicated. So Matsumoto computes K2 of a field. it's given by the tensor product. This is the tensor product. So K star, that means the units. So those are two abelian, this is an abelian group. So I can take the tensor product with itself. And then I just quotient out by this relation. I set all pure symbols A tensor 1 minus A to be 0. A kind of complicated object, but you can get a sense of what's going there on there. And this isn't going to really play a role much for our talk, but since we're in the neighborhood, I just thought I would define Milnor K theory here. You basically just take the tensor algebra on the units and then mod out by this equation. This is a homogeneous equation, so you get a graded ring, which happens to be graded commutative. Okay, so that's just a little rapid background on super classical algebraic K theory. And I'm somehow zoomed in too far, there we go. And well, hopefully I can zoom in just a little bit more. Quillen then in 1972 defined K groups of a ring in general, the higher K groups. This is given by the plus construction. So you take this this infinite general linear group we saw before. You take its classifying space. So this classifying space is a K pi 1 or a K GLR 1, and then you do this operation to it called the plus construction, which is sort of a minimal way to kill this maximal perfect subgroup given by the elementary matrices. And that's some magical construction. And Quillen takes the nth K group for n at least 1 to be the nth homotopy group of this new space. Now, I think it's one of the great, I don't know, insights, mysteries of mathematics that this is like a sensible and important thing to do. Let me just remark here that that this plus doesn't change the integral homology, and that's an important. So the homology of BGLR with, say, integer coefficients is isomorphic to the homology of the plus construction, this K theory space, and that'll come up briefly later. So it somehow doesn't change the homology, but it radically changes the homotopy group. So one of the backgrounds of this project is that there are almost no commutative rings for which the full calculation of these K groups is known. One case is given by Quillen. So this theorem from 1972, in this theorem, Quillen computes the full K groups of finite fields. And these are almost the only known full calculations. I think it probably is the case that it's the only known algebraic extensions of FP are probably the only known fields where there's a complete computation. And so they're given by this formula. So again, I'm skipping n equals 0 because we know that's isomorphic to the integers, so we can just skip it. The higher K groups are 0 in even degrees. And in odd degrees, there are these funny numbers, z mod q to the I minus 1. How might you remember this? Well, note that K1 of FQ is isomorphic to the units in FQ. And you know that that is isomorphic to z mod q minus 1. Okay, so that's the I equals 1 case of this result. How does Quillen prove this? It's kind of an insane proof. I mean, it makes heavy use of group homology, which I'm trying to sort of preview here. It also uses so-called Brouwer lifting of modular characters to get from modular representation theory to actually at least virtual complex representations. And once you work around that enough, you get a map from this plus construction of BGL into BU, the classifying space of the complex unitary group. And then you have on BU this Adams operation, psi q, and it turns out that this map exactly identifies BGLFQ plus with the fiber of 1 minus psi q on complex K theory. And from that, you figure out exactly how that acts on complex K theory, and you pick out this computation. So beautiful, yeah, kind of landmark theorem, and in a certain sense, still the only base case that we know of any calculation of K groups. Any other K groups that have been computed use this as an input. Okay. So let's see. Now let me say a little bit about how it's done in practice these days, which is to break K theory up into different arithmetic parts. And that's because there's a pullback square. This would be true for any spectrum. It's called an arithmetic fracture square. Maybe I should have written that somewhere. And it says that there's a pullback square from the K theory of R with Q coefficients. This means the rationalization of the spectrum, and the homotopy groups are just given by the rationalizations of the homotopy groups of K theory. And then down here, I get the product of the L completions for all primes. And then I see I missed a, and then in the bottom right corner, we have this profinite completion, and then I have to rationalize the completion. Now, so the general strategy now is to somehow look at these pieces separately, try to compute them, and then reassemble them. And I'll give some examples. Now, let me just, I have a little tableau here about these different parts and the state of the art today a little bit, which we'll see a little bit more of. So amusingly, the upper right-hand corner, the rational part, this is the hardest part from the perspective of today's machinery. This is the part that has to do with algebraic cycles, and in particular, the Hodge conjecture, and then the so-called Beilinson-Soulé conjecture, which is about certain vanishing in ranges of motivic cohomology groups with rational coefficients. And basically, we have no idea. So I don't know. This part for a general ring R is very mysterious. On the other hand, the last 50 years have seen a huge amount of work on the profinite completion part. And that really splits up into two different regimes. One is when L is invertible in the ring R. And here I just say a bunch of names: Suslin, Gabor, Thomason, Bloch, etc. This is now, from today's perspective, governed by the Bloch-Kato conjecture, which was proved by Rost and Blavatsky. And it says that, at least for reasonable rings R, if L is invertible, you can compute the K groups using a Tull cohomology, at least in high degrees with respect to the dimension of the ring, or technically the Tull cohomological dimension. And so that says, using that, and that's a theorem, we can get, if you can compute a Tull cohomology, then you can get information about the L-adic parts. And that's basically how any computations of the K theory of integers are known, is to use Iwasawa theory and compute the Tull cohomology of Q, basically, which is going to tell you enough information, but not everything yet, to compute those K groups. The other regime is when L is not invertible, and that's kind of the realm of what's called p-adic Hodge theory these days in this context. And that's been studied by Geisler, Levine, Hesselholt, Madsen, and then all of the recent work of Bott, Morrow, and Schulze, Clausen, Matthew Morrow, and many others. So we have these three regimes here, and I'll get to how this looks in a specific example in a moment. Okay. So seems like this is kind of running off the page. Oh, that's because it is running off the page. Okay, so basically what our work is about is trying to answer this problem, which So in this original conference proceedings where Quillen's paper on higher algebraic K-theory appears, there's a list of problems compiled by Gersten, and problem 20 from that list is due to Swan. So Swan asks specifically if you have a ring of integers in a number field to compute the K groups of R mod I, where that quotient is finite. The first example of this is, of course, just C mod P to the n itself. And there are some other examples. So you can, the general form of this, well, basically you can split K-theory commutes with finite products of rings. So you might as well assume that this R mod I is an Artinian local ring, in which case it can also be written as a quotient of a ring of integers in a p-adic field, OK, modulo some power of the uniformizer. And all such are given by this formula here. You basically take Witt vectors in the residue field, adjoin a power series variable, and mod out by an Eisenstein polynomial. An Eisenstein polynomial is just one where the top coefficient is a unit, a p-adic unit. And then P divides all of the rest of the coefficients, but P squared does not divide the bottom coefficient. If you learned Eisenstein's criterion in algebra, then these are the ones to which that applies. And so these are all irreducible. They define all algebraic extensions of QP, and their rings of integers, mod powers of the uniformizer, give you all of these rings. So just an example, like adjoining a pth root of, an eth root of P gives you a ramified extension, or some cyclotomic extensions, but then you don't use the cyclotomic polynomial, but sort of shift of it. And so let me just take this opportunity to run down some notation that'll be here in the rest of the talk. I'm going to look at a finite extension of QP. Its residue field will be K. It's a finite field with Q elements. Q is P to the F. F is called the residual degree. E is the ramification index. That's, in other words, the degree of this Eisenstein polynomial. The total degree of the extension is the product of those two numbers, E and F. OK is the ring of integers. It's a discrete valuation ring. And I'm going to just let pi \var pi for LaTeX users to be any choice of a uniformizer for us. One of the interesting things about the theorem we proved later on is, or the algorithm we construct, is that it actually sort of depends. It's sort of sensitive to pi in a weird way that hopefully Akim will tell you a little bit about. Okay, so we want to compute these K groups in this setup. Obviously there's infinitely many of these. Just looking at this, that's clear, but there's even more. So we'll get a little sense of that later on. Okay, any questions at this point? That's the end of first part. Okay. Well, let me just run down very quickly the L not equal to P part of the story, which is going to let us reduce these calculations to Quillen's original computation. And so we'll see that there's no additional prime to P information when we're trying to compute the K theory of such a thing. So we don't have to worry, we won't have to worry about prime to P information. And right. So first of all, Suslin computed the K groups of separately closed fields with L-adic coefficients when L is invertible. And basically they're 0 and odd degrees, and they're just given by ZL in non-negative even degrees. You can ignore this twist by I. That's just keeping track of the Galois action on the K groups. So technically what's appearing here is the ith twist of the Tate module of the units of K. So now already in Quillen's 1974 ICM address, he realized that if one could have some form of descent for K-theory, then, so basically Quillen sort of foresaw this theorem, and he conjectured that there should be a spectral sequence going from the cohomology of the Étoile cohomology of X with coefficients in these sheaves to the K-theory of X. And if that were the case, then at least in principle, you could compute this up to computing the Étoile cohomology, and then of course up to computing some spectral sequence. Now, this expectation, or sort of the best version of this, the best version that could be true, is actually a theorem of Rost and Voevodsky. It follows from their proof of the Bloch-Kato conjecture. And it does indeed say that in high dimensions, if you have a reasonable, meaning kind of regular Noetherian with finite Étoile cohomological dimension residue fields, then in high K-theoretic degrees, you can compute the K-theory by computing the cohomology and the Étoile cohomology of the spectral sequence. So the L prime to P sort of setting is really, really nice. I think that's the moral of the story. A related fact about how it's nice is this theorem of Gabor called Gabor rigidity, which says that if you have a Henselian pair R comma I, so meaning that the pair R mod I satisfies the conclusion of the Hensel's lemma, you can lift solutions of polynomial equations from R mod I to R under some assumption on the derivative of the equation. So, and if L is invertible in R, then the L-adic K groups of R and of R mod I agree. And so if we look at what that means in the setting that we care about, where we have a p-adic field K, well, so complete rings are in particularly give Henselian pairs. And so OK is p-adically complete. The residue field is little k. And so you see that the L-adic K theory of OK is the same as the L-adic K theory of the finite field K, which is computable by Quillen, as we'll see in a moment. But that's also true for these intermediate rings, OK mod pi to the n. And so these groups are Quillens. And there's nothing really extra to be gained. We don't need to do any further analysis to understand these groups in the prime to P setting. And so let me just do a couple examples about how this fracture square now looks. If we look at the base case of FQ, the K theory of FQ, well, you notice it's all torsion except in degree 0, where it's given by Z. So if we rationalize that spectrum, we just get the Eilenberg-MacLane spectrum Q in degree 0. Similarly, you'll note that everything above degree 0 was prime to P torsion, right? The groups were of the form Q to the I minus 1. So when I P complete, those are all totally invisible. And I just get the P completion of degree 0. So that's again ZP sitting in degree 0. So I get the Eilenberg-MacLane spectrum ZP in degree 0. And for other L, then the nth homotopy group of the L completion is given by the L-adic integers in degree 0. And then it's just the Z mod the L part of Q to the I minus 1, whatever that is. Okay, L might or might not divide that number, but the prime decomposition involves L to some power, and I take Z mod that power of L to get the nth K group. And so that's a complete kind of picture of this fracture square that we need. And you can use that to kind of easily recover the integral structure. Now, in the OK case over here, I basically don't know anything personally about the structure of the rational K theory of p-adic rings of integers. I'm not, off the top of my head, I'm not sure anything's known, but I could be wrong. It's going to be pretty complicated. Even if you think about the ring of units, right? You're going to have, I mean, you get massively things that are massively not finitely generated over the integers. I'm not quite sure what there is to say. Gabor rigidity, though, tells us that the L-adic K theory of OK for L not P is just the L-adic K theory of FP of the residue field, FQ. And then the p-adic K groups are much harder. So the p-adic K groups you can attack in two ways. You can either use Quill and Lichtenbaum and Bloch-Kato and Iwasawa theory and all that stuff. Or these were also computed using trace methods by Hesselholt and Madsen. Should have mentioned that here. In a 100-page annals paper where they do a bunch of computations in about TR and TC, and they take that approach. It's a very hard theorem. And so here we're interested in the following thing. So OK mod pi to the n, it's a finite ring. Actually, that implies that all of its positive K groups are torsion. That sort of follows from the fact from homological stability for the group BGL, the fact that the plus construction doesn't change homology, and then a Leray-Serre spectral sequence. And Weibel attributes this to someone named Cuckoo. I'm not quite sure who that is. So that means there's no, all the higher K groups are finally generated abelian groups. So again, the rational spectrum is Q, the L-adic spectrum is the same as the residue field, and now we're just really left with understanding the p-adic part of the K theory, and that's what our work is about. So it's really about understanding the p-adic K theory of rings like OK mod pi to the n. So, wow. Let me rapidly, well, let me say a little bit about how to tackle something like that. So nowadays, the way to do this is not so much using group homology and the plus construction, but a totally different approach, which is adapted for this, for understanding the p-adic part when P is not invertible, and especially for P-complete rings. And it's built by starting with this THH construction, which is a version of Hochschild homology relative to the sphere spectrum instead of to the integers. It's a spectrum with S1 action, and it has a lot more structure. So it has sort of genuine fixed points with respect to the subgroup CP to the n. And using that, you can build these theories called TR and TC. So TR is a limit of the CP to the n fixed points. It turns out that there's a residual Frobenius action on TR, and TC is the F equals 1 eigenspace for that action. This is an incredibly rapid introduction. And this is called topological cyclic homology. It's classically it was a very difficult construction. It was a difficult thing to understand. One of the things we'll see in a moment is that it's gotten a lot easier. But first, let me mention this sort of main theorem, which is going to make everything that we want to do work. So it says that somehow, if you have a ring R, which is not too far from K, meaning that I have a map from R to K, which is surjective and has a nilpotent kernel. Okay, so it's a nilpotent extension of K. An example to bear in mind would be like something like Z mod P squared down to Z, but down to FP, or FP adjoin X mod X squared to FP. Or larger quotient, Z mod P to the n. Okay, so in that setting, I get a pullback square of spectra. So there's a trace map from K theory to TC, and roughly speaking, the horizontal fibers agree. So the difference between the K theory of R and the K theory of K is the same as the difference between the TC of R and the TC of K. And that gives you a new strategy for computing new K groups. Namely, find some base ring whose K theory you know, compute its TC, compute TC of your mystery ring, and glue it all together to get the K theory of that ring. And TC, it has a homological flavor. So it turns out that you can compute it using things like differential forms or maybe de Rham-Witt forms. And so it seemed, it's better than group homology, where you can't exactly name elements of random, high homology or homotopy groups of this plus construction. So most progress in K theory of p-adic rings comes by actually computing these TC groups. So let me just in this square, I highlight the importance to us. What that means is that for us that the K groups, the p-adic K groups of something like OK mod pi to the n are actually just exactly the connective cover of the TC groups of that ring, the p-adic TC groups. And so what we're going to do, in fact, in this project with Hakim and Thomas is we compute the TC. And by this theorem, that computes K theory. On the right-hand side, I have a couple examples. So it turns out that this TR of K, which is a priori a spectrum, ends up being an Eilenberg-MacLane spectrum. It's WK in degree 0 if K is a perfect FP algebra. And then that has a Witt vector Frobenius, and so TC of K is just WK 1 minus F. And so that implies, for example, that pi 0 TC minus K is equal to ZP, at least if spec K is connected. Otherwise, it's some number of copies of that. Pi minus 1 is WK modulo 1 minus F. So if K, for example, is an algebraically closed field, then this term vanishes and I'm just left with ZP. And everything else is 0. In the smooth case, these TR groups are related to de Rham-Witt forms, which are used to compute crystalline cohomology. And so TC has some connection to crystalline cohomology. And TR of rings of integers like OK was at least attackable enough for Hessel-Holt-Madsen to eventually compute TC of OK, which is close to the K theory of OK. So that's the original computation of the p-adic field case. So, okay, so that's how this sort of used to work. But this is the main structural theorem that still today is the crucial input into most calculations. Nowadays, there's a sort of alternative approach to this complicated world of cyclotomic spectra and TC, which is given by this new theory of cyclotomic spectra due to Nikolaus and Schulze. Basically, they observe that THH itself has a so-called cyclotomic Frobenius map. It's not an endomorphism of THH. Instead, it maps it to the Tate-CP construction on THH. It's some kind of Frobenius, but of course it's not Frobenius exactly because these are not FP algebras. There's also always a canonical map. I can always include homotopy CP fixed points into this Tate construction. And then TC minus is what I get by taking homotopy S1 fixed points. TP is what I get by taking Tate S1 construction. And then by applying homotopy S1 fixed points to these two, I get two different maps from TC minus to TP, at least ignoring P completion issues. And TC is just the fiber of that. That's a theorem. The theorem is that the previous definition given in terms of this 1 minus F action on TR agrees with this definition. It's not obvious and it's not particularly easy either. the payoff is that this turns out to be vastly more computable in general, and than the TR groups. And so that's at the basis of a lot of this recent work of Botmore and Schulze. So I run here through on this page just how this looks for FP itself, or for K, I guess, a perfect FP algebra. So first of all, the homotopy ring of THH is a polynomial ring on a degree 2 generator. It follows that the homotopy S1 spectral sequence has to degenerate for degree reasons, because there's just nothing in any odd degree to receive a differential. And so this B lifts to a degree 2 class of TC minus, and there's another degree -2 class coming from the cohomology of CP infinity that lifts to degree -2 class. Those multiply and they give you an element in pi 0. It turns out that pi 0 is the Witt vectors and that they multiply to the element P. And then you get TP by just inverting V. So you get this computation. The right hand side gives you what these CAN and phi maps do. CAN basically sends B to P times V inverse and V to V, and it's WK linear with respect to these presentations. Whereas phi is Frobenius semilinear, where I use the Witt vector Frobenius, and it sends B to V inverse and V to P times V. So when you look at this equalizer diagram and you try to compute what is TC, so in a non-negative degree, you have a basis generator B to the I, and you have a map that sends X times B to the I to this formula, P to the I X minus F of X, where F is the Witt vector of Frobenius. And something similar happens in negative degrees. The formula is just slightly different. But note that if in either case, if I is at least 1, then you have something that's like topologically nilpotent, namely it's P times something minus an isomorphism. Okay, and that means that everything away from when I is 0 vanishes, and you recover this exact thing that we saw from the TR perspective, namely that it's just all that matters is the I equals 0 case of this, and you're exactly doing 1 minus F on the Witt vectors. So that's a kind of remarkable, I mean, in this particular case, of course, this is more complicated, but maybe the thing to say is that it's easier to prove these theorems than it is to prove that TR up here is given by W of K. So even though the result is a bit more complicated, TC minus and TP, they aren't Deilenberg plane, they were easier to compute, and we still had enough power to compute these CAN minus phi maps and hence compute TC. Is there a question?
Oh, I have one very quick question. On the previous slide, in the explanation of the map phi, there's a sequence of, I think, letters that I can't quite make out. What does that say right underneath the arrow labeled phi?
Oh, it's F semilinear.
Semilinear, thank you.
Where F is the Witt vector Frobenius. Thanks. Okay, so I wanted to explain, because Akim is going to use prismatic cohomology. Somehow this ends up being how we are going to answer this question. So I wanted to explain very briefly how that comes up. So in their second paper, Botmore and Schulze introduced these quasi-symptomic rings. So these are certain p-complete rings that are just somehow nice. So they're bounded, meaning they might have p torsion, but it's bounded p torsion. So at some point there can be p to the 30 torsion, but then at some point it stabilizes, and there's not 30 p to the 31 torsion that's not p to the 30. Okay, so they're derived p complete. Under the bounded hypothesis, derived p completeness is the same as classical p completeness. And the cotangent complex over ZP has Tor amplitude in 0, 1, which is a way of saying, this is just a way of saying that it looks LCI. It looks LCI modulo P. So these are like P complete lifts of LCI rings or something like that. And an example of such a thing is OK mod pi to the n for all of the cases that we care about. That's all that really matters here. There's also a notion of quasi-regular semi-perfectoid spelled out here, which is that a ring is quasi-regular semi-perfectoid if it's quasi-syntonic. Additionally, it emits a map from a perfectoid ring. And finally, on S mod P is an FP algebra, so it has a Frobenius, and you want Frobenius to be surjective. That's the semi-perfect condition. I'm not going to define perfectoid, but think of things like OCP, the ring of integers in the P completion of the algebraic closure of QP, or FQ is also perfectoid, at least by my convention. Okay, so examples of these quasi-regular semi-perfectoids would be OCP modulo P to the n. That's like an infinite version of this problem that we're considering. And they define a site, the quasi-syntonic site. And and basically everything is locally quasi-regular semi-perfectoid. So an example of a cover is one of the following. We do OK mod pi to the n to OCP mod P to the power that it has to be, basically n over the ramification index. And the point very briefly, because I'm a little short on time, the point is that all of these theories, THH, TC minus, TP, for quasi-regular semi-perfectoid rings, they all end up being concentrated in even degrees. It's a calculation they do. And so using that, they define a filtration, the double speed Postnikov filtration. That gives you a new filtration on all of these, and then they descend it to an arbitrary quasi-syntonic ring. And I've listed the associated grades of those filtration here. So this is the ith graded piece of the Nygaard filtration on absolute prismatic cohomology, the ith filtered piece on Nygaard complete absolute prismatic cohomology, Breuer-Kissen twisted by I and then suspended by 2I, and so forth. This Breuer-Kissen twist is analogous to the Tate twist we saw in Susslin's theorem. And then on TC, it's not quite, it's even only locally on the quasi-syntonic site. And you get these complexes ZP, these are the syntonic complexes. And they have some kind of definition. They're the fiber, it's a cyclotomic-y thing. It's the fiber of CAN minus phi on something extracted from TC minus and something extracted from TP. And the point is that these terms have to do with prismatic cohomology, which is given the site theoretic formulation by Bott and Schulze. And the important thing is that means that you can compute these potentially by ignoring all topology and actually just doing prismatic cohomology. Okay, so now we come to the actual K theory of OK mod pi to the n. There's kind of two regimes here. On the right hand, I have a special case which was completely solved by Hesselholt and Madsen. Namely, take a finite field K adjoins Z and mod out by Z to the E. And it turns out that using trace methods and TR and so forth, Hessel and Madsen were able to completely compute the K groups. These were revisited by Martin Spears in 2020 using the Nicolau-Schulze approach, and then by Yuri Salima last year by computing these quasi-symptomic complexes, these symptomic complexes. What's known is that all of the even groups vanish, and the odd groups, their structure is known, but it's complicated, but their order is easy. It's Q to the I n minus 1. What's n? I guess, well, in this notation, E minus 1. For these rings of integers, very little was known, basically. K1 is units, K2 was studied about 50 years ago. K3 was analyzed about 40 years ago, and then sort of finished up about 30 years ago. Brun, 20 years ago, figured out the K groups for Z mod PBN. There seems to be maybe better to say KR. When n is small with respect to P minus 3, and Ingoldfight extended that and proved this theorem. Now let me just, in the minute or so remaining, let me say what we do and I'll tell you, and that's what. All right, it's my last slide, so it's perfect. And this is what Akim will expand on next time. So in our case, this associated graded, so the ZPIs, these symptomic complexes, filter TC, and TC we know is what we need to compute K theory. And they vanish outside of a range. So they're concentrated basically in degrees 1 and 2, which means that this spectral sequence associated to this filtration vanishes. And in particular, it means that the K groups are actually just these symptomic complexes, the cohomology of these symptomic complexes. Okay, so it's now enough to compute these symptomic complexes. And what we do is we give an algorithm to compute these, an algorithm to compute these like on a computer. Using that, we prove this quotient relation, which generalizes work of Ingoldfight. We don't know that the even K groups vanish, but we still get this relationship about the ratio. And then we prove that for large I, the even K groups do vanish. And that proves that for large I, we get the exact order of the odd K groups, which reduces the computation of the orders of all K groups to a finite problem. Namely, compute up until this bound, until you hit this bound. You just use the algorithm, actually spit out the computations until you get this bound. And then you've computed all of the orders. The cyclic group structure is much harder. And if people ask the right questions, I'll show how that looks on a computer in a moment, but I'd better stop now. So thanks a lot for listening.
Any questions?
So I don't want to interrupt somebody else asking the right question, so I'll try to be. Is there any hope for the kinds of techniques you're looking at to analyze like derived rings where there's stuff where there's nilpotence in positive degrees or ring spectra?
I haven't thought about that specifically. I will say that probably our methods can be used to compute the K groups of any finite LCI ring. Any finite commutative ring, which is local complete intersection over the integers. It would not therefore surprise me that for certain sort of simplicial commutative rings, the same methods would hold, namely with some finiteness conditions on the cotangent, and finiteness and boundedness conditions on the cotangent complex. I have not thought about that very carefully. That's a great question.
Other questions?
I had one which is somewhat orthogonal to maybe your actual goals in this talk, but it was hard to resist when with all the background that you were giving. You gave us a very tight connection between the K theory of p-adic rings and the TC of those rings, particularly for number rings over ZP. Is there any chance that knowledge of all of that information for all primes might tell you something about TC of a numbering over Z?
Right. Great question. It's kind of subtle, and this is, there's this Leopold's conjecture. Are you familiar with this?
At some point I was, but not right now.
I mean, so you might hope to do exactly what you're doing and resolve all remaining questions about the K theory of integers. But let me show you why you should be a little afraid, which is something I learned about while doing the background research for this project. So let's say OK is now a ring of, well, OK ring of integers in a number field. So of degree D. So then I can look at OK into its P completion. And then this splits as a product of some like local rings, like local ones, OKI.
Sure.
Now I can look at the units OK cross, and I can P complete them. And inside here is a big lattice. Well, it's a finite index subgroup of the form ZP to whatever the rank of the units, which is given by some theorem. R1 plus R2 minus 1. And I can map this into the units of these product OK cross. And this is roughly speaking rank Z to the D. And of course, D is at least R1 plus R2 minus 1. The conjecture is that this map is injective. AKA that some p-adic regulator is non-zero. And I mean, you can ask now about a higher dimensional version, higher K group version of Leopold's conjecture in higher K groups, which is something I'm interested in pursuing. But if we don't know it for K1, so I think the state of the art is we know it for like abelian extensions of Q, and for some abelian extensions of maybe real quadratic extensions of Q, the usual kinds of conditions that come where you can actually solve these things. And so the fact that this is hard makes me worried about using these methods to directly attack rings of integers in general. But my pessimism could be unwarranted. I haven't thought too carefully about it.
Okay. Is it then just because I think of the kind of regulators that you're talking about as living on the more sort of number theoretic side of things, is that can you sort of rephrase this in some sense as an interaction between the p-adic Hodge theory side of the story with the rational story? Is that?
I mean, yes. I mean, it must be about the kind of right leg of this map in the arithmetic fracture square.
I see.
Roughly speaking, and how to glue these different symptomic and motivic complexes together and how that works. But I don't know anything kind of, I don't know anything more specific to say at the moment. It's something I'm excited to think about someday in the future where there's time.
Thank you.
Okay. Any more questions?
Yeah, I have one question. What is it about these quotients that makes these like symptomic complexes actually calculable in some sort of algorithmic fashion? I mean, I don't really know too much about prismatic cohomology, but I wouldn't, maybe I wouldn't expect that outright.
Right. I guess there's two things. The first of all is that there's, they're not far. So we compute them using prismatic envelopes, which is some kind of prismatic deformation of divided power envelopes. That's part one of the calculation. And that doesn't quite give the symptomic complexes, but it gives the symptomic complexes in a relative sense. And then there's some sort of Hopf algebroid, which tells you how to descend from those prismatic envelopes to the actual prismatic symptomic to the actual prismatic cohomology, and then to compute the symptomic complexes. So really, it's the magic of prismatic cohomology. But if you want to know maybe what the main insight is that lets this work, it's that these have an extra filtration on them, namely the p-adic filtration. And that p-adic filtration gives a notion, you can use that to develop a notion of filtered prismatic cohomology, and then everything else in sight picks up an extra filtration. And then it just turns out that that filtration is not finite on prismatic cohomology itself, but it does turn out to be finite on the symptomic cohomology. That's the crucial idea. Once you know that at least if you could compute everything, there would be an algorithm because it's reduced to a sort of finite problem. And that's what we do. So you could probably do this for other rings like WK, adjoin some numbers, and mod an ideal, which is sufficiently nice so that the result is a finite commutative ring. The algorithm would be more complicated and it's certainly not implemented. But in principle, this would be doable, at least to compute the symptomic complexes. You would then have to struggle with the fact that they're bigger. And so the sort of symptomic to TC spectral sequence doesn't have to degenerate. And that I would have nothing to say about at all. We're working in a case where it just degenerates for free.
Is there time for one more question, Sasha? Or
Okay, go ahead.
yeah,
Yeah,
So-
because I have to turn off
Yeah.
really quickly. To
this
run to
this
my
begs the
class.
question of, so you mentioned that there's this filtered notion of these symptomic complexes, or is there some way in which that is compatible with filtered analogs of THH and all of these other things that are popping up? Or,
Yeah, absolutely. That's exactly how we knew that such a theory should exist, or why it was in our minds.
right.
Well, at least I have to close this Zoom part. Well, this Zoom part, the room part of the session, because I have to run with my computer to teach.
Okay.
but, if there are any other questions on Zoom, on other Zoom parts of the story, then please, I can leave and let somebody else to pick up.
Sure, you could make me the co-host, Sasha.
Okay, all right, great. Okay, so thank you very much, Ben, for the wonderful State of the Union address on K-theory.
Yeah.
I'm stopping recording now.
Thanks.
And
Thank you, Ben. This was really lovely.